Okay. Now there will be two parts to this talk. The title of the talk about how to calculate fermion correlations and how to infer from these properties of CP non-conservation in the strong interactions. And this has been our original approach to the problem. This is from the path integral. The second part is when we look into theta vector and wave functionals. So this is not published yet, but it should be pretty much contained on these slides. It uses canonical quantization, and I think it is important there in order to get the full picture on the problem, and also canonical quantization is needed in order to construct equilibrium field theory, which should also be of relevance here for this audience for obvious reasons. So this is the outline of the first part. I will review what are the CP odd terms in the Lagrangian and how do they connect with observables in inverted commas, because here I stop constructing observables at fermion correlations. Of course, you can go further and connect it then all the way to the electric dipole moment of the neutron, as was explained very concisely by Carlos yesterday. And one intermediate step here are effective operators, and this is of course the famous 't Hooft vertex that we are going to construct here by comparison with these fermion correlations. Okay, so in order to start with the construction, we then look at the topological term in the Lagrangian, and I will review a few things, and I will in particular discuss how what kind of boundary conditions on the path integral lead to integer topological charges, because that is of importance for actually the outcome of whether there's CP violation in the strong interactions or not. Then 3 to 5 is actually then about the construction about these fermion correlations. It's going in several steps. First of all, we need to have a Green's function in the presence of a single instanton, and then in the presence of multi-instantons, and then we need to take account of the quantum fluctuations at leading order for these instantons. So we need to make interferences, and first we carry out interferences within the topological sectors. And up to this point 4, I'm not deviating from anything that has been said hundreds of times in the field before, but then the crucial point will be in part 5, where we interfere among the different topological sectors. And I will argue that it is mandatory to take the infinite space-time volume limit first before carrying out this formation of the topological sectors. And this then decides the question of indeed whether there's CP violation in the strong interactions or not. So here, of course, there are two CP odd contributions to the QCD Lagrangian. First of all, there's this topological term or theta term, which is E dot B essentially, and therefore it is odd under charge parity conjugations. And here we have this chiral fermion mass term. And if alpha is not equal to 0, then the sign contribution here is proportional to gamma 5 of this exponential. And this is then also a CP odd term. Of course, just having a CP odd term in the Lagrangian does not really lead to the conclusion that there are CP violating observables. One necessary condition for having a CP violating observable is that there's a rephasing invariant. And indeed, there is a rephasing invariant, which is famously theta bar. I go to this on the next slide. If we do chiral transformations on these fermion fields, this theta bar is non-zero, and theta bar is CP odd. So it's a necessary condition for CP violation, but it's not a sufficient condition for CP violation. What you also see is that since theta is connected to alpha here via the chiral anomaly, it is mandatory that theta behaves like an angle. Okay. Now, once we, in some sense, integrate out the gluons here in this topological term, we arrive following 't Hooft by an effective vertex, which is the famous 't Hooft vertex. And it is written in terms of these determinants, if you wish, of these fermion fields. So, and you have products here over the flavor of the various fermions. So here is some coefficient. Of course, this coefficient can't be reliably calculated in the dilute instanton gas approximation, at least not if you want to apply it to the real thing of QCD that we have in nature. But I believe that the essence of the problem of whether there's CP violation or not should not hinge on the question of whether the theory is confining or not, which is of course something one can discuss. But I mean, the principal question I think can be covered in the dilute instanton gas approximation. If you don't believe that, then I refer to Carlos's talk yesterday, but also to the second half of this talk today. Now here's the CP violating phase, which is here Xi. Because I want to leave open what it is. And of course, if we look for these CP violating phases, or what could it be in the effective theory, the usual argument is we go back to the original theory and we do these chiral field transformations, which I've written down here. So we multiply the spinors with e to the I gamma 5 times beta. And then we demand that the Lagrangian shall remain invariant under these transformations. And then, of course, we have to change what is m or what is alpha, and we have to change what is theta. And under such transformations, alpha and theta change in the following way. Theta bar remains invariant, and this means that we need, since this here has to, this Xi has to transform with e to the minus 2 and f beta, because this is directly following from the Fermion field transformations. We can round up the two suspects for Xi, and which is just theta, and the other option is minus alpha bar. So this is important because typically it is just assumed in the literature without spending any time on this point that this parameter Xi is just theta. In fact, the only calculation of this has been done in this 1986 paper by Toft on how instantons solve the U1 problem. Otherwise, I think it's just an assumption that is not being really discussed. The other thing that is perfectly consistent with these chiral symmetries and their breaking is minus alpha bar. So this is the phase from the quark mass matrix. All right, and then the next question is, how is this effective Toft vertex constructed? In principle, it is coming from integrating out the gluons. In practice, what one does, or what I think is the most transparent way of doing this, is to compare it with Fermion correlation functions. And so we construct the effective vertex in such a way that it generates here these Fermion correlations, and these Fermion correlations are something that can be calculated from first principles. So yesterday, essentially, Carlos has shown without instantons how to compute this in the coincident limit. And now I'm going to show how this is following in the dilute instanton gas approximation. Okay, and so what is the implication now for a CP violation? We should compare this with the leading contribution to the two-point function, which is one that is already there in the zero instanton background. And this is, of course, just given by the inverse of the Dirac operator, which we all know, and this is of the following form. Of course, you can do this integral, you get some Bessel function, but the essential point here is that the term that breaks chiral symmetry here comes with e to the I alpha gamma 5. So this means that if Xi happens to be theta after first principle calculation, we would say that there is CP violation in the theory. If Xi turns out to be minus alpha bar, which is also a possibility to this end, then we would conclude there's no CP violation. So to simplify things here, I don't think I take anything essential away from the argument, is that I don't want to have these products and sums associated. I just take one flavor from now on. Okay, so let's review a few things on the topological term, because obviously this is related and important. Yeah, these are arguments we've seen this week already on several occasions. So the topological term turns out to be a total divergence. So there's K, which you can call topological current, if you wish. And then the integral over K over a spatial surface you can refer to as the Chern-Simons functional. So since this is equivalent to a surface term, we may expect that if this flux here of this current through the surface vanishes, it doesn't have any impact on the evolution of the quantum expectation values. But does it vanish? Well, of course it doesn't, because we know that there are these BPST instanton solutions which go down as 1 over x cubed. And this is just the volume of the 3-sphere. So in general, there's no reason to expect that it vanishes. And of course, one can also quantify this because one realizes that if one looks at these BPST solutions, that for large distances, so I'm always working here in this part of the talk in Euclidean spacetime. So for large distances in this R4, the instanton field configuration becomes a pure gauge. So omega is here an element of the SU2 gauge group. And then the topological current, of course, you don't have to memorize this expression, but the thing is, it is essentially, this integral is a Haar measure over the group space, and it measures essentially how often the configuration space, that is like the R4, is mapping around the vacuum manifold of the group, which in this case would be SU2. And of course, here I have scaled it down to U1. And therefore, these anti-instant configurations always give us winding numbers of ±1. So we can anticipate that there are contributions through the action, even though a theta term is a total derivative. But then, of course, not all configurations that we have in the path integral are just instanton solutions. So why is it still so that we have to have integer topological sectors? But first of all, since theta can be viewed as an angular variable, we have to require that this is an integer, because here you can see it. Well, I guess you can see it here. If you exponentiate this with a factor of I, you need to have this 1/16 pi square f tilde to be integer, so that theta behaves as an angular variable. So do we have to put this in by hand? Well, fortunately not. This is already built in the path integral. So if I take the point of view that I don't constrain the boundary conditions on the path integral, and then I ask which contributions to the path integral yield non-vanishing contributions, then these come from a minima of the Euclidean actions and from fluctuations about these minima, because we also have to take account of the quantum fluctuations. And then by the arguments that I've given before, these vanishing physical fields at the boundary of infinite volume are pure gauges. And for these pure gauges, as we have seen in the last time, no matter the last slide, no matter whether these pure gauges are the limit of BPST instantons or just pure gauges from whatever configuration is inside, we know that we get delta n e to be an integer number. But this crucially requires that we consider an infinite spacetime volume. In a finite volume, at least, I mean, save, of course, periodic boundary conditions on a lattice. But if you have like an actual surface where you want to put boundary conditions on, there's no such restriction to integer topological sectors, unless, of course, a professor putting these boundary conditions on a surface is a good enough reason. Yeah, so what is the consequence for us here? We have said we take the attitude here that we don't constrain the boundary conditions, but we know that we only get contributions to the path integral from these finite saddle point configurations and fluctuations about these. And this means we need to sum over all topological sectors delta n, and by this topological term, we weigh these by this phase here. Okay, now this is the background. Now let's go and look at the calculation. So we want to calculate fermion correlations. I've already outlined this a bit. We first calculate the Green's function, which is the inverse of the Dirac operator in the background of one instanton. And then as a second step, we need to go from the Green's function to a correlation function. And therefore we have to basically interfere over all quantum fluctuations. Okay, so the Euclidean Green's function satisfies just this Dirac equation here with the source term. And then there's a spectral sum representation for this. And actually, it's easy to see what the spectral sum representation means, because if you, I mean, S is just the inverse of this Dirac operator here. And if we act with the Dirac operator here on these eigenmodes, so I've written here an eigenvalue equation. So psi lambda are the eigen functions of the Dirac equation. Lambda are the eigenvalues. When we act with the Dirac operator on this thing, then we get another factor of lambda. Numerator and denominator cancel, and then we have a completeness relation, and so we saturate the delta function. Okay. I've written this for m equals 0 here, but actually, of course, this is ill-defined because of the presence of these fermion zero modes, because there's the Atiyah-Singer index theorem, and this tells us that the number of zero modes differs, the topological charge delta n equals the difference between the number of right-handed and left-handed zero modes. Okay, in the presence of a single anti-instanton with delta n equals -1, there's only one left-handed zero mode, and the solution has been found by 't Hooft. It's actually like a simple solution, not a simple algebraic form. And then what we can do is to get a good approximation. I mean, one can do this a bit more exact, but it's not crucial. Let's say with the terms that are transparent, we take out the zero mode out of the spectral representation, and then we just regulate this with a small eigenvalue, which is now just given by the mass, and it's a complex eigenvalue in the presence of this CP odd phase. Okay. Now we can do this in a background of n instantons and n bar anti-instantons, and so we just add all these instanton anti-instanton contributions together. So I'm saying that these instantons are sitting at locations x nu or x naught nu, and the anti-instantons are sitting at locations of x naught bar nu. And then from the Green's function here, I just take the dominant contribution for small mass, which is given by the first term here. And then this is the contribution which is basically suppressed non-perturbatively by the action, by the tunneling action I need to do to create instantons. And of course, I must not forget the leading contributions, which is just what is happening in the background of zero instantons. So anywhere between these instantons, roughly, I have this thing, which is just the standard Dirac propagator. And here I have these extra contributions because of instantons and anti-instantons. Yeah, so this is something that has been applied before, a long time before in the business of dilute instanton gas. And so the significance here is that if you remember what this S0 instanton is, it has this phase alpha here, and now the phase alpha also shows up here. So there's an alignment between the Lagrangian mass and the instanton-induced chiral symmetry breaking. So there's no CP violation here at this stage. But in some sense, this is also to be expected because the theta phase has not yet entered the calculation. And we only see this at the late stage, how theta may or may not enter the calculation. So now let's proceed and carry out the interferences first within the topological sectors. So within the topological sector, the topological charge delta n is fixed. So by the way, this is like our idiosyncratic notation. So delta n, of course, is what normal people call Q here at this conference, yeah. So we need to sum overall instanton anti-instanton configuration n plus n bar with the constraint that delta n is fixed. Then we need to move around these x0 nus, so all these locations of all instantons, anti-instantons, and also there are some remaining collective coordinates associated with the gauge symmetry. And this is essentially what is called the dilute instanton gas approximation. Of course, one can also do it without the DIGA, as Carlos has shown us yesterday. And this is how it looks like. So this is a bit technical, but I think the meaning is very transparent. So this is our correlation function now in the fixed background. We obtain it by integrating out the gauge fields and the fermion fields in a path integral. So here's our action here, S. And here there's this operator we want to calculate. And then we carry it out in the Gaussian approximation in the background of these instantons. And so you see what happens here. So first of all, we have then combinatorial factors because we cannot distinguish instantons and anti-instantons. Then we have to integrate over these collective coordinates. So there are zero modes associated with the fact that we don't change the action when moving around the instantons and anti-instantons. So this is coming out of the calculation here. So we have to integrate this over the space-time volume for all n and n bar topological objects, essentially. Then we have additional measures and Jacobian factors dealing with gauge symmetries and collective coordinates. And then this S of n n bar here, this is just this propagator here in the background of the fixed instantons. And here, of course, we are integrating over the coordinates of all these instantons. Then we have the Euclidean action. So this is the price we have to pay for having these n plus n bar tunneling events. And then here are some reduced one loop determinants from the gauge field and from the fermion. And what we've done here is that we've pulled out from the fermion field the phase alpha, yeah, because from the Fermion determinant we get from the zero modes, of course, also like a factor of m to the I alpha. And basically the definition of the fermion determinant here of the reduced determinant is such that it doesn't bear phase. And so the phase is pulled out here. And so what you see is that this phase here, which is CP odd, let me finish the sentence, is universal. So it is basically multiplying here the whole enchilada, yeah, with instanton and zero instanton contributions.
How depends on the number of flavors you have?
Okay, so here I've written this for, I think,
yeah.
So I think if you generalize this to NF flavors, of course, you would get just a sum here of, so alpha would be multiplied by NF essentially. Otherwise, it wouldn't really change, yeah. I mean, what else would be changing? Yeah, I mean, you just have a larger number of fermion zero modes that you regulate, and then from the determinant for each of the flavors alpha, you get for each of the flavors you get one phase factor. But this is then absorbed in the definition of the general definition of alpha bar. So do I have it here? Yeah, because here alpha bar is basically essentially this the sum of all the phases from the different individual quark masses. Yeah. But of course, yeah, if you think of it from, of course, not like directly related to this problem, but from a dynamical perspective, then you would, of course, see that if you pull out all the fermion masses, you get additional suppressions from fermion masses, essentially. Yeah. So if you think of taking chiral limits or something, yeah. Okay, so you can do the same thing for the partition function. And so again, we have these collective coordinate integrals, we have the action price we have to pay, and then we have the whole phase here. Yeah? And so at this level, again, within a single topological sector, we have a global phase here, and this happens to be the same global phase there. So there's no CP violation yet, because theta hasn't really entered the game yet, because we have fixed the topological sector, and no matter what we do in the topological sector, since the integral over FF tilde is fixed, there's no dynamical impact on whatever is happening there. Okay, so then it remains to integrate out the locations of the instantons. Don't have to be too technical here. It just means that, so we have to sweep over all of the zero mode locations, and then we end up having a function which we call h. And this function h will not depend on the average coordinate, because we are just averaging the instantons now over all space. So it will not depend on x plus x prime. It will only depend on x minus x prime, essentially. And this gives us like then this first like one instanton-like contributions to the fermion correlation functions. In addition, we can also like get rid of these remaining factors of, I mean, the fermion correlation function is not a gauge invariant object, so we can also average that out here at this stage. And so what we find here is then a correlation function for fixed delta n. After integrating out the collective coordinates, we haven't summed over all these n instantons and bar anti-instanton configurations yet. Okay, so here are the instanton contributions. So we have n instantons and n bar anti-instantons. It's chiral, they go with PL, left projector, right projector. Then we have the zero instanton contribution. Since we are integrating over, or we have integrated over these n and n bar instantons over spacetime, we get powers of the spacetime volume. And then here we get the power of the spacetime volume -1, because this is already absorbed in this construction of this h function. Okay, there are combinatorial factors again, because instantons, anti-instantons are indistinguishable. And there's this factor kappa, which again is the price we have to pay for the tunneling. So it goes with n plus n bar. And then we have the thing that we're interested in here, the CP odd phase. Okay. So now we can look at what this means. So first thing we might worry about is that here the power of the spacetime volume is different from there. But of course, if you calculate what is the expectation value of n, so kappa is essentially the likelihood per unit volume to have an instanton there. So you can calculate the expectation value of n simply this way. Again, instantons are indistinguishable. And then you find that this expectation value is kappa times Vt. So you get exactly what you desire, because then you want to have here, of course, an instanton suppression of the instanton effects, which is an extra factor of kappa, which you don't have here. and you get the same power of the space-time volume, so they have the right scaling with the volume. Okay, what you also see is that, of course, if you increase the volume, then the fluctuation in n, or same as in n bar, gets ever sharper. So it goes down with the square root of the space-time volume. And this means that essentially in the large volume limit, this term and that term will be the same. And this you can also see when you carry out the sum, because in the sum you get these modified Bessel functions. And these modified Bessel functions have the property that if you take the argument to infinity, or this x, this factor of I in here, but if you take here the space-time volume to infinity, they essentially become independent of the index. Yeah, so they have the same thing here, and I think this is very reasonable because, yeah, in the large volume limit you're not really sensitive to this little difference here. Okay, again at this stage, everything that's CP violating is multiplying everything here. So there's no relative CP phase between S0 instanton and this contribution here. And yeah, by this argument, this already points that in an infinite volume limit, we should expect alignment, but let's carry this out. Yep.
Okay. So you mentioned, I think I first mentioned you, but so this 2-point function is not gauge invariant.
Well, at this level, it's already like gauge average, because this is when we have this H here and we sort of integrate over these gauge collective coordinates.
Yeah, well, that's my question. So yeah. Can you, is this okay? So if I have a correlation function which is not gauge invariant, then I do a gauge transformation and integrating over all gauge fields. Is this some sort of, what does it mean somehow? So in other words, so if I have a gauge invariant quantity and I do a gauge transformation, I integrate over all the gauge transformation, I think this I can understand somehow.
Right.
So, but now this is not gauge invariant. So if I do a gauge transformation, I imagine that the resulting propagator has changed. And so, yeah, if you can comment on that.
I mean, but I mean, it carries indices still in the gauge group, yeah. And so this gauge averaging, I mean, you find objects of this type in these papers by Schiffman, Weinstein, Sakharov, yeah. Okay. Okay. So maybe one would have to look into that later, yeah. So there these integrals are carried out.
Okay.
Yeah.
Okay. But we can also discuss.
Yeah. Okay. Good. So the same thing again can be done in at the level of the partition function. And so the partition function then also turns out to be a modified Bessel function with index of delta n. And this form here of modified Bessel function in respect to the partition function has been found also by Lord Wheeler and Smilder before, basically from some opposite approach. And so what we see here is that this factor here, basically, if we take averages, it would cancel out. So therefore, it's crucial to see whether this cancellation remains even after we interfere the topological sectors. Now, I mean, there's one thing that is not really in the mathematical presentation of this talk, but it is kind of driving my intuition here, is that the question is whether interference between topological sectors can be observed, because what one can do is one can think of, you can derive these two partially reducible effective actions, if you wish, and then you get equations of motions for expectation value of quantum fields in each topological sector. And you know that they are none the wiser about whatever happens in the other sector, yeah. So they're completely independent. And of course, you can still compare the correlation function in each of these sectors, and then you can interfere them at the end of the day. But then, in principle, the observer, like Philip in his laboratory, can also model him as a correlation function, yeah. And so the observer is sitting in a sector, and then who's interfering these different worlds of our experimentalists, yeah. Who's there to do that? So one need to have some super observer to do that. And in principle, okay, it will turn out that with this order of limits, that actually what you see in each sector is the same thing. So it is a bit of a moot point. But on the other hand, I think it's also like a severe thing that indeed, the barrier of action is infinite between the sectors, and you would not be able to see any change in the dynamics in this sector just because all these other sectors are also there. Okay, so anyway, this turns out to be immaterial in the limit of infinite space-time volume, but I just wanted to put it out here. Okay, so let's now come to the decisive point. So these interferences in these topological sectors, why are they immaterial? So far we have our Fermion correlator in a fixed topological sector. Oh no, we have the one in the fixed topological sector, which is just the numerator term here. And now what we're going to do is we are going to sum over all these topological sectors. Now to have, to legitimately argue to have an integer topological charge in a topological sector, we need to take the space-time volume to infinity. And so this means that we have to take the space-time volume to infinity first, and then we look at the series of all of these sums, of all of these partial sums with ever increasing cap n that we eventually take to infinity. And yeah, so here you recall again this form of the zero instanton propagator, and by the argument that I've just given, since this phase of this phase that I've highlighted here in brown is universal, it appears here and there, and since in this limit everything is independent of the index of these modified Bessel functions which appear here, 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 what we get is this result. And all what shows up is alpha and not theta anymore. Yeah. So there's no relative CP phase and no CP violation. If we were to order the limits the other way around, as Toff did it in 1986, without, of course, discussing the order of limits, you can go back and do the sum without restricting it to fixed topological sectors. And then you see that you have a simple exponential series here. And these sum up to the familiar form of cosine potential, essentially in the correlation function and also in the partition function here. Okay, and then what is decisive here that you see is that you have basically huge destructive interferences and everything. So what was aligned before, so in each sector n and n bar are of the same order because the volume is large. And then you have large destructive interferences between all of these sectors if you do the calculation this way, and you're left behind with actually here different coefficients that would signal CP violation, which, by the way, may also explain why it is hard if you set up the calculation like this on the lattice, why it is hard to see this, because it relies on huge destructive interferences. Okay, so then we get here CP violating observables simply because here we have e to the I gamma 5 theta, and here we have still e to the I gamma 5 alpha sitting there. Okay, but this order of limits is not a choice, but it is dictated by the fact that we have to impose the boundary conditions for the topological sectors at infinity, because these are basically just the configuration that the path integral with open boundary conditions selects. Now you can ask yourself what is happening for quantum mechanical systems in a crystal. I know that I have these Bloch waves which have these different energy states that are indicated here, and I'm telling you for QCD they are not there. Well, for a crystal you only have a finite number of degenerate minima, and therefore the order of limits is not really an issue, yeah, because then the sum over this topological sector has a natural cap. But I'm also this will also be closely related to what I'm going to talk about in the second half of the talk. Okay. So I don't know whether I should go at length in the effective operators, because I think Carlos has explained this very nicely yesterday, but just the summary, if we take the space-time volume first before carrying out the sum of the topological sector, our 't Hooft vertex has this form. And if we are carrying out if you're doing it the other way around, we get the canonical result that would then motivate axions and such things. And here's, of course, also the generalization of the 't Hooft vertex again for NF flavors, but you've seen this already on the first slide. And of course, then I'm not going to this in detail now. You would write down the effective chiral Lagrangian, and then by just the Spurian arguments and the matching, you would be forced to have here for this phase psi that is coming in front of the determinant term that would give you the eta prime mass. You would have to put either theta or alpha bar depending on what you have done here, yeah, what you think is right. Okay. So this would be the first half of the thing, and so maybe there are short comments already or technical questions. Because then I'm gonna.
I can ask a question.
Yeah, yeah.
When you write down the sum of all the sectors of the propagator, is the weight depending on the charge on the sector included somewhere?
Yeah. I mean, okay. So the weight is essentially a function of. I mean, okay. There's a phase and there's a real weight. Yeah. And the.
Yeah. I mean, not. In, I think next slide.
Yeah.
Maybe I'm missing something. I don't know. Maybe just too quick. No. Yes. Here. So you see, you're summing. Is that weight depending on the sector?
Yeah, I mean, there should be in principle a mild dependence on delta n, yeah, but this goes away in the infinite volume limit. So, I mean, that's precisely the point, yeah. So these objects will depend on delta n unless you take the volume to infinity, because they depend on these modified Bessel functions. And the argument of the modified Bessel function essentially is this determinant, this exponential factor from the instanton times the spacetime volume. And if you take the spacetime volume to infinity, all of these modified Bessels get independent of the index. And the index is related to delta n. Yeah? So you have floating around delta n plus 1, and delta n minus 1, essentially. So yeah, it's included, yeah, but it goes away.
It's flat in infinite volume.
Yeah, it is included, but it's of course crucial. That's a crucial point. Yeah, it goes away in the infinite volume limit. Yeah. Yeah, okay. I mean, this is the first independent of theta, and then of course theta is then still. I mean, it's still. I mean, the theta is not in the modified Bessel function, but the theta is here. What's explicitly there? Yeah. So there's a weight. I mean, depending on what you call now a weight, there's a weight which is a real number, which is in the modified Bessels, and then there's the phase. Yeah. But I'm not dropping anything at this stage. Yeah.
That's kind of on the role of temperature, because it seems that what you have argued here is that temperature plays absolutely no role.
Yep.
I mean, I understand the energy effect, but when you write for a rate of 20, if the argument is weekly, if you go into the frequency, like I have no way to distinguish from a temperature from zero temperature to 50%.
Yes. So.
Yeah.
Well,
That's another thing, but
yeah.
The temperature in general.
You're doing your temperature,
Okay.
Temperature, because when we see those things, and we don't distinguish any temperature. The temperature is the material.
Right. So I mean, the logic of what I've done so far, but I'm coming back to all these points in a minute. But the logic of what I've done so far is that I say that the Euclidean path integral is like one fundamental way of defining the theory. Yeah. I can take this attitude. Yeah. Yeah.
And then temperature is defined by changing volume, pressure volume to infinite, and you can find a temperature and constant. But all the formulas I have seen, there's no way to make such distinction.
Right. Yeah.
Overshadowed by volume infinity.
Yes. I mean, for the finite temperature system, you would, of course, impose periodic boundary conditions. And antiperiodic for fermions, right? And then you could take the point of view that if you take this one, if you take beta to infinity, you take the temperature to 0, and then you have the infinite volume, yeah. But of course, the question is, I mean, we need to make, of course, something to be discussed. So what is the connection with the first principles of the theory? Yeah. So what I'm really calculating here. Of course, I can say I can also like say that finite temperature field theory, as defined as the path integral with periodic boundary conditions in time or antiperiodic for fermions, is some sort of fundamental definition of something. Yeah. And then, of course, I would do something different here. Yeah. But so the question is really, yeah. Sorry?
You have done a part integral, you can only have partition function.
Yes, but what I've done here is that I've taken the limit here of the space-time volume to infinity. Yeah, so I've not done here really like a finite temperature calculation in the first part of the talk. Yeah. Yes.
In the final temperature, you can then send the beta to 0 and t to 0 and then beta to infinity, and then you can send it to back.
Yeah, okay. I mean, I could also take here the attitude that my V is infinite and my T is finite, yeah? Where T, of course, now T is the inverse temperature. And then, of course, in principle, if I follow this, then I would get two different answers, depending on whether V is finite or V is infinite, yeah? Because if I say that for some reason, if V is finite and then my space-time volume is finite, and then I get the result with CP violation. Yeah, of course. I mean, it's just what the mathematics tells us. Yeah, but I think, and then of course one should start to wonder, why do I get two different answers if I do this and that? But then I think the thing is we have to go like one step back and ask ourselves, why do we construct the finite temperature effective action in a certain way? Yeah. And this is what I'm going to relate to in the second part of the talk.
The ground state will be different. So I mean, in one case is the thermal state, which you could say the thermal state you could have more transitions. Indeed, this is another question I have. In the case of the Fallon, of course, you say that there is a change, so you can change if you want your topological number.
Well, I mean, we had this discussion yesterday with Mike Tipper. I mean, I was asking the question. I think it is correct that for periodic boundary conditions, so in all dimensions, you have also conserved topological charge. Yeah. So from the perspective of the path integral, the topology is always conserved. But from the perspective of the evolution in the path integral, yeah. So what is conserved is, of course, the winding number over the volume, yeah. But if you take spatial slices, then of course on two different spatial slices, you can measure different Chern-Simons functionals. And this is so if you like a Fallon is happening in between two spatial slices, this is precisely what is changing the Chern-Simons functional. Yeah.
Well, of course, the total charge is conserved because then we change the Baryon number in the case of the Fallon, so over the line on the left of the tool.
Yeah, but I think I mean, maybe it's a bit of a semantic problem. I'm trying to say, because if you say a Fallon occurs, yeah, and something is changing topologically, yeah, you're right, of course, yeah, but you have to. So there's the winding number contained in the entire volume, in the 4 volume, and there's the Chern-Simons number, which is the flux over the Chern-Simons current through the 3 volume, yeah, okay. And so if you follow the time evolution of, let's say, one path, one field configuration, you sum over in the path integral, the Chern-Simons flux is changing all the time. Yeah. But what is basically said is if you have these vanishing field configurations at infinity, the Chern-Simons flux through infinity is not changing. Yeah. Yeah. But it's conserved by the boundary condition. It's always integer. Yeah. And a similar thing you have also on the lattice, yeah. So you like average over these field configurations. So you have your Monte Carlo gives you some trajectory in field space, and if you take a slice, three-dimensional slice, you will see that. I mean, of course, in principle, there are all these numerical things that are there. But in an ideal world, in the continuum limit, you would see that the Chern-Simons number is not conserved. But what is strictly conserved is the integral over ff tilde over the entire volume. Okay, so yeah, so yeah, I said, I mean, of course, these questions point to this thing. It's important to have the full picture because this is like relating to the Euclidean path integral in R4, and I think it's like somewhat expected or accepted that this is sort of some fundamental definition of the theory, but like how do we go to finite temperature? And okay, so I don't write it down here in words, but if you like, my way of like explaining how to construct equilibrium field theory is that we want to calculate the trace over e to the minus beta h over the canonical partition function. And so in some sense, we need to have a canonical quantization. Of course, like for gauge theory, it is a bit of an awkward thing because gauge fields don't like to be canonically quantized. And in the end, we have a path integral expression, which is then, especially in lattice field theory, it is gauge independent again, yeah. But in principle, we have to go through this bottleneck of canonical quantization because we have to make some sort of sense of what does the trace of e to the minus beta h means. And h is then really meant to be an operator in the canonical formalism. And this is what I'm going to like talk about now in the second part of this talk. So I first review the standard story of these theta vecua. And as we all know, they are introduced as a superposition of an infinite number of field eigenstates. So infinite number means that they are not properly normalizable, and field eigenstates means that they are not readily be identified with a vacuum. So this leads to things that need to be discussed, which I will discuss. And then I think it is of interest in order to decide these questions or to understand these questions, to look into the canonical quantization of the gauge field, what is going on. And so then one ends up that one needs to have some wave functional representation of the state rather than like these like sums over e to the I theta n. And then one has to deal with gauge redundancy because these large gauge transformations lead us to different gauge field configurations, but they are physically redundant, same thing. And so I think this gauge redundancy, especially in this case of like a discrete redundancy that brings you back after some finite trajectory in field space to the same point, resembles a situation when you put a point particle in quantum mechanics on a circle. Yeah. Whereas typically in this business, one has the picture of more like a Bloch state where one puts the point particle in a potential which is exactly periodic. Yeah? Of course, you could argue they are the same thing, but I want to carve out in what respect they are not the same thing, because in some sense we are expecting that if you have a crystal with Bloch states, you have a different energy spectrum as for a particle on a circle. But actually it is a bit subtle to pin down exactly the reason why the spectra are different. And so I propose why these are different spectra, and then in the end I roll back to gauge theory and draw the consequence there. Okay, so the standard story with the theta vecua is, okay, I don't have to go through this again. Basically what we do is we say, we construct some gauge independent states by taking the sum here. And then if we carry out a large gauge transformation that changes n by this discrete number of units, this state doesn't change, but for pure phase, which is then given by e to the I theta. Now, this is not the ground state of the theory yet. So in principle, we would need to like evolve this to infinite time, which then would be the connection to what I've done in the first part of the talk, because I need to like evolve everything to infinite time to have a projection on the ground state. And only after I've done that, I can do some business of interfering these states. So this is another reason for motivating these order of limits. So there are two shortcomings associated with it. The one is that I have already just mentioned here. So these pre-vacua are not like the ground state readily. So one could take the time to infinity to project on the ground state, and then, but then one like has to like go through the first section over again, or one can construct a wave functional and look into the general properties of the wave functional. And this is the point of view that is basically taken in these original papers by Jacques. The second thing is, which is maybe even less appreciated than this question of that these are not really field eigenstates, are that these states are not normalizable in the proper sense, because literally in all of these papers you see expressions like this, that the theta vacua are normalized to a delta function. Now, of course, we teach quantum mechanics, we tell the students about the postulates of quantum mechanics, and there we say physical states are members of the Hilbert space. But these states, which are not properly normalizable, are not members of the Hilbert space, but they're just approximations to actual Hilbert space states. Yeah. But since we are like already having here issues with orders of limits, maybe approximation is not good enough. So there seem to be like two obvious resolutions if we have to deal with these non-normalizable states. One is, well, we construct wave packets, which then would mean that we are not having an exact peak in theta, but we would have like an ever so slight spread. Yeah? But I don't think that this is an acceptable solution here, because we want to, of course, have that gauge invariance is exact. The other option that comes to mind is that one does some gauge fixing. So if you think of it like a particle on a circle, then of course you have your redundant description from the coordinate phi to phi plus 2 pi n. And then you can say, okay, I just border about like one fundamental domain, 0 to 2 pi, and then I don't have any issue with non-normalizable states. And so I think that this first option can be like excluded from the outset. So I'm concentrating here on the second one. So how does this canonical quantization look like for the gauge field? I mean, we typically teach it in introductory relativistic field theory lectures for quantizing the photon field. So basically, we take the canonical momentum of a field A, and then we are all familiar with the fact that the canonical momentum is just the electric field. But then if you add a topological term to the action, which is maybe a bit less known, is that we get a contamination of theta times the magnetic field in non-abelian theory. Well, of course, yeah, this is in principle, you would also have it in QED, but in QED it's immaterial. Okay, so then we need to construct an operator representing pi quantum mechanically by imposing the canonical commutation relations. And then again, we have a choice here. So this is coming from basically taking the variation of the Lagrangian with respect to A dot. And here I can basically satisfy this commutation relation for any differential operator delta with respect to delta A. But I can add again an arbitrary factor alpha here. So this alpha here has nothing to do with the theta. I can just do this. It just satisfies the commutation relations. And then I put this back into the Hamiltonian density. So I replace all the temporal derivatives of the configurations with respect to the canonical momentum. And what one arrives at is the following thing. So the theta is the original thing that is coming from the Lagrangian. And the alpha is basically this coming from the ambiguity that we have in defining the canonical momentum. Okay. Now, then we can follow Jacques of what can we make out of this when we have wave functionals in field theory. Now we have a functional psi. This is like the wave function, and it lives on the field configurations A. And we are looking for solutions of the time-independent Schrödinger equation, because this would then help us to basically make sense of the trace of the canonical density matrix. Yeah. And so we know that these states must be eigenstates under these large gauge transformations. Yeah. Because these gauge transformations are unphysical, and therefore they must transform under large gauge transformation at most by a phase. Yeah? And this phase can be chosen to be, I call it here theta prime. Yeah? Okay, so now we have three things in the game that do the same thing. We have theta from the Lagrangian, we have alpha here, and we have theta prime. And of course, only one of them is maybe physical. Yeah. Okay, from all of these considerations, one can see that basically this problem or this feature we're talking about is present in some class of quantum mechanical systems. Namely, if we have a wave functional psi of v, and v could just be like a space-time coordinate or can be a field configuration now, and then we apply a translation of v so that essentially we have a unitary operator, we apply this on the wave function, and we get the translated wave function. And then we know that if there's a periodicity here, we have to we should be able to find these eigenstates of the translation operator. And then by like applying several transformations after one another, this has to hold for integer n. And the correspondence here I'm making is, of course, that I draw a correspondence between v and the vector potential, and my unitary operator is then given by these large gauge transformations. Okay, then we define here a functional n of v with the property that if we apply a translation, then we go from n of v to, it changes by 1 unit. And of course, this N of V is nothing in gauge theory, it's the Chern-Simons function. When I take the state and I apply a large gauge transformation, I change the value of the Chern-Simons function by 1 unit. And in general, one can then constrain the states to be of the following form, that they are basically functions which are, or functionals which are periodic in T. So psi of T of V is just psi of V for the minor psi. And then all the non-periodicity, the phase is then isolated in this extra vector here. Okay, so if you look at this abstract formulation, you see that it applies to gauge theory as well as to a particle on a circle. So this is really the essential point. So let's dumb this down to a particle on a circle. So the wave functionals with these periodicity conditions, I mean, the way this is written here, of course, we recognize Bloch states, and that's probably what people have also seen like 50 years ago when they first thought about that. Now, Bloch states live on a crystal where the translated point is a physically different side from the original point. Yeah. In contrast, in gauge theory, we would say that the translated configuration is a redundant description of the same configuration, of the same physical configuration, which would correspond to a shift of phi to phi plus 2 pi n, where n is an integer on a circle. Now, an ant that is crawling around these potentials would see that this is the same situation as that one, yeah, because it's just repeating itself. But is it such for like a quantum state? Yeah, I don't know what your intuition is here, but of course, when one thinks about this, maybe the intuition is that on a crystal we have, after all, a different spectrum than on a circle. Yeah, in particular, we won't really have the freedom of like having basically a continuous energy band. Yeah, but if this is the case, why is this the case? Well, one thing that the circle does for us is the truncation of the inner product immediately resolves this issue with the normalization, because we can like normalize it to 1 instead of a delta function, and we can calculate operators, and we could make sense of the trace of the density operator. Okay, so let's look at these quantum states on a circle. So let's look at the Lagrangian, and here I introduce a parameter omega, so which is basically an angular velocity, and I put a potential on a circle. So the potential is basically the barrier between the different integer Chern-Simons numbers, so between the different vanishing physical field configurations. And then, of course, if you square this, you can forget about the omega square term. It's just a shift in the ground state energy. But you have a term, the cos term gives you a total derivative, which corresponds to a theta term then in the action. And then you see that same features that we have seen for gauge fields 5 minutes ago. We calculate the canonical momentum, we get omega here. We calculate the Hamiltonian, so that we have an extra term in the Hamiltonian. So theta survives when we construct the Hamiltonian. And we can construct the canonical momentum operator. And the canonical momentum operator, we are free again to choose such a angular velocity term, theta-like term. Okay, so let's try to get some intuition about what is happening. So let's look first at the case where omega b from the momentum operator is just absorbed in omega. So we're looking at a Hamiltonian with a general angular velocity here. And now we are going even simpler. We are just looking at the case of omega equals 0. And then we think, okay, we can solve the time-independent Schrödinger equation. Yeah. Maybe the natural thing to do here would be to impose periodic boundary conditions, but it's not clear yet mathematically why we would have to do that. But I will try to carve out the reason why this is the correct thing to impose periodic boundary conditions here. But now compare this with a potential moving at a constant angular velocity, omega v. And then we know that if this is a solution to the static configuration, we immediately know that this is a solution to the moving configuration, the co-moving one. Okay. But in some sense, this is not a time-independent Hamiltonian operator, and this is then also not really a time-independent Schrödinger equation. Now what we can do is we can basically do a Galilei transformation to put the potential of the second case at rest again. Yeah? And then, so a Galilei transformation can be obtained by exponentiating an infinitesimal translation operator, and you can convince yourself that this operator here, with pi being the canonical momentum and phi being the angle, induces indeed these shifts. And then at the operator level, it acts as a unitary operator, and it has the desired property. And at the level of the wave function, it also acts as a unitary operator. But since the potential is an operator, it does something different to the potential than the wave function. Yeah, so that's a bit of a subtlety that's arising here in quantum mechanics. And on the state, what it does, it basically adds here, if you wish, some angular momentum, and it adds some kinetic energy. Yeah, so it makes physical sense. Now we can apply this to this solution here and basically undo this annoying omega b. And then what we find is that we have a function here that has angular kinetic energy, and it has some angular velocity. And let's absorb this here, this angular velocity, this angular momentum in psi prime. Yeah. Now, if we absorb it in psi prime, this psi prime has a different periodicity than the original psi because of this term here. Yeah. And then this solves our Schrödinger equation in the following way. Yeah. So we have one thing is we have now an intuitive interpretation of this theta term because it basically physically corresponds to moving our potential around the circle. The other thing is, if for some reason, and I haven't given a reason yet, we choose for this solution here periodic boundary conditions, then this means that, well, the solution here is no longer periodic, but in some sense, the omega that is in the psi prime compensates the omega that is now in the Hamiltonian. Yeah. So in some sense, this removes then the CP violation. Yeah. So if this has anything to do with QCD, then CP violation is gone. So why would we choose now periodic boundary conditions here? Okay, so now let's look again at our Hamiltonian. And for simplicity, let us set omega to be 0, because we just wonder now about these periodic boundary conditions. So intuition may tell us that's the thing to do, but what reasons against it is that, well, after Galilei boosts, the wave functions do not need to be periodic anymore, but they are still valid wave functions. And of course, if we argue from the invariance of quantum mechanical expectation values, again, the periodicity is only fixed up to a phase. So we can't use any of these arguments to fix the periodicity. So what is then the reason to fix the periodicity? And the reason turns out is the consistency in the time evolution of operators. So here we have a Heisenberg equation of motion for an operator that depends on e to the I phi. I'm writing here e to the I phi because e to the I phi is the gauge invariant thing, if you wish. Whereas I could also write equally well phi, it wouldn't change much, but then it would not look gauge invariant. Okay. Then this can just be calculated. So the relevant commutator comes just from the kinetic term, no matter what the potential is. And so we get this answer here, which is not yet telling us very much. And now let's assume we calculate just this object here, where phi, okay, eventually we take phi to be a real periodic function, but just as a matter of fact, if you write it here in this funny way, we see that this expression here is a total derivative in phi. Yeah. Okay. Now, let us assume, so we're looking now for solutions to the time-independent Schrödinger equation. So we want to know what the energy eigenstates are so that we can compute the trace of the density matrix. Yeah. So then we know that these expectation values of operators for energy eigenstates should be time-independent. So we would impose that 0 is d with respect to dt of O of phi. So when we calculate this expectation value. And this expectation value is now of the following form. Now, if we assume that these wave functions here, psi, that represent our states, are of this form here, where phi is a real function with which is periodic, then we see that with this extra factor here, we precisely have this desired periodicity. So this means that, I mean, this omega here is coming from the theta term that is residing in the Hamiltonian. Yeah. Okay, so if omega is 0, then of course also it is 0 here. But if we add omega to the Hamiltonian so that we have a theta term in our game, then this means that we must have an according phase dependence in our function here. So we have a compensation. Yeah. So this means that if we impose that these equations here are consistent, I mean, okay, by the way, I didn't finish the argument. So of course here we have then, if psi has this form, we are exactly here back to this form here. And then we integrate over from 0 to 2 pi. It's a total derivative. We only have boundary terms, but the boundary term vanishes because we assume that this is periodic here. Yeah. Okay. So, okay, this is like some abstract mathematical argument. It's not difficult, but of course, I don't expect that you validate it in 2 minutes. But the conclusion here is that for the eigensystem in the Hamiltonian, it follows that if omega is 0 in the Hamiltonian from the outset, the wave function is periodic. And if omega is not equal 0 in the Hamiltonian from the outset, well, the wave function has this additional phase in its periodicity, but in such a way that the omega phases are basically compensating because it corresponds to just a particle moving along, and it's the same as just changing the coordinate system. Okay, so what does this mean physically or intuitively? So for the intuitive explanation, think at the moment about the case where omega is 0 at the level of the Hamiltonian, yeah? Because that is what makes sense to us. It's just a potential on a circle. Okay, and we can always achieve this by boosts, yeah? So we take a system and we just boost with the Galilei transformation our omega away in the Hamiltonian. And then, however, we can still have like a phase under these shifts in our wave functional, yeah? On a crystal, this would have a very clear interpretation because it would be a crystal momentum, like a Bloch state, yeah? Okay, and so what we have done now, just on the previous slide, is, so here is phi, and we have this redundancy here. And what I plot here is, or what I draw here is basically the wave function, yeah? And I calculate some expectation value by taking an integral over the green area. So because of gauge fixing, I just decide to integrate from 0 to 2 pi because I deal with normalizable states. Now, what we have just calculated is that if omega is not equal 0, then in general, this d with respect to dt of O of phi is also non-zero. Yeah. However, if I look at it this way, this is a completely static situation from the perspective of the wave function. Yeah. So there's a time-dependent phase, but it doesn't enter in the expectation value of the operator. Yeah. So this is telling me that d with respect to dt is 0. What I've calculated on the previous slide, it means that it's not 0. I can't assume because here I have the wrong periodicity condition. So there's an inconsistency here in this perspective. If I take a different perspective, so if I go on a crystal and I have Bloch states and a wave packet, then of course I need to take it seriously that I have to integrate over the full axis here. Normalizability is taken care of by the fact that I have to build wave packets. And then of course, it still holds what I've calculated on the previous slide, that this d with respect to dt is non-zero because it is like at the level of an operator. But it can be non-zero because now I'm integrating over the full thing. Yeah. And of course, I can have something like going in from infinity and going out at infinity here. Yeah. So basically, a wave packet has a moving hull moving along with a crystal momentum on the circle, whereas I have to reject this picture on an actual circle. Yeah. And so I think after thinking about this for weeks, I think this is the way how to pin down why spectra on a circle are different from spectra on a crystal while having exactly periodic boundary conditions. And now, yeah, this brings me to the end. Oh, well, not just to review, let's think what this means for gauge theory. We have this very similar behavior here. In general, we have to go into the game here with a general theta here and with a general theta vacuum. So given by what I have here in the Hamiltonian and in the state. However, if this applies to gauge theory, the argument that I've given, and it should apply because normalizability is, I mean, it's a fundamental postulate of quantum mechanics, then the only possible choice here in the states is that this theta that I have here has to be the theta that I have there. And if I do that, then I can remove it by a Galilei transformation. And the Galilei transformation I can construct by looking at the Chern-Simons functional, and basically my unitary operator that does the Galilei transformation is this one here. It removes theta from the wave functional and it removes theta from the Hamiltonian. And then there's a theory which does not have any CP odd term and therefore no CP odd observable. Yeah, so this is the conclusion. yeah, I think it is not there, and I hope I also give good reasons for this. This is based, I mean, we're not taking this lightly. It is based on, I think, some serious challenges to the standard calculation, because what really would be the reason to impose topological quantization on a finite surface? Yeah, surface. So of course on the lattice we can have still topological boundary conditions or configurations because we don't have a surface. Yeah, and of course it can also be viewed as a tool to go from to infinite times at 0 temperature to project on the ground state. So the theta vector, I think they are, one needs to address this and think about it in order to make sense of yeah, the density matrix, canonical density matrix. And yeah, a problem that one may identify here, which I don't think has been spelled out in the literature, is that these states are not properly normalizable, which contradicts with the postulates of quantum mechanics. So how does the standard procedure agree with quantum mechanics, I'm asking? Gauge fixing leads to normalizable states, but then for consistency, we are restricted to, if you have this point of view, by consistent time evolution of the operators, we are restricted to CP conserving theories. But also I think, I don't know whether it appeals to your intuition, but I don't want to argue with intuition. I think my intuition is telling me that the spectrum on a circle is different from the spectrum on a crystal. So the resolution here would be that we simply don't have these theta vector in the canonical approach.
Thank you.
Thanks so much, Bjorn. As you know, very interesting results. There was a question from, let me see, I think from Skyler. It says he had to leave the meeting, but maybe Bjorn can comment in the afternoon discussion why the wave packet solution that is commonly used for basic quantum mechanics and E&M solutions, for example, to obtain normalizable superposition, is not acceptable.
The audio is also back on.
Yeah.
Okay, so
this is not on though, but we have to switch on the. Okay.
Okay. Yeah. Okay. So, right. Of course, there's no problem on a crystal not to have an exact momentum eigenstate. And in fact, since the crystal is finite, unless you happen to be able to buy an infinite crystal somewhere from a mine in Russia, then of course translation invariance will be broken and we have momentum eigenstates. But of course, for gauge theory, we think that equivalent gauges should be like an entirely redundant description, and therefore we have to require that all observables are independent under gauge transformations, and this means that these quantum mechanical wave functionals must only change up to a pure phase. And I mean, this extra phase I have also argued away in this talk with the consistency of the equations of motion. I mean, maybe another technical point here to say is that, I mean, I didn't really think about it before, so maybe I should also share this, is that if you have a theory with a continuum spectrum, or like a partially continuum spectrum, then like a mathematician doing functional analysis would tell you that the eigenvalues are part of the spectrum, but the states that are not normalizable are not part of the Hilbert space. Yeah? And so the construction is then that you qualify like an eigenvalue to be part of the spectrum if you find a normalizable wave function that is arbitrarily, whose like eigenvalue equation arbitrarily closely satisfies the exact eigenvalue equation. Yeah. So this means that the picture is, I mean, you can really think of this as momentum eigenstates in a translation invariant background. These momentum eigenstate wave functions, they're not physical, you can't normalize them, but of course you can, the momentum is still part of the spectrum of your Hamiltonian. And you can construct, of course, your physical states as wave packets, and they can be arbitrarily close to the real thing. Yeah. But only close, yeah, not quite there.
Are there questions in the audience or at home? Well, as you know, Bjorn is going to be here, and also in the afternoon we're going to have a discussion. Scott is going to be here, and so maybe it's time to go for lunch. And I want to thank Bjorn again, and I'm looking forward to a discussion this afternoon, so we can go into the details.